Those of you who have taken multivariable calculus will remember the multivariable Taylor series. What is a Taylor series? Well, my inimitable colleague, Professor Rob Greist, who has the world's best calculus MOOC, teaches us that we should think about nice functions as being very, very, very long polynomials, meaning that you can expand nice functions by Taylor series into higher and higher and higher degree polynomials and get better and better and better approximations. This is called Taylor's theorem, and the notion of nice is captured formally by the word analytic. Go take Rob's course if you're interested in what this means. From our point of view, what it means is that we can expand a function f of x at any point x in the neighborhood of some interesting point x star using the value of the function at x star plus a linear approximation achieved by taking the derivative of the function at x star and multiplying the difference from that x star point by that derivative, and then forgetting about a bunch of remainder terms called the Taylor remainder, which are guaranteed to get very, very small very quickly. We'll think about this second term as the linearization of the nonlinear function f of x. And let me remind you that capital F at x star is the Jacobian. It's the matrix of partial derivatives evaluated at that point of interest. The linearization of f at x star turns out to be extremely important and valuable in the world of dynamical systems. If you'll recall, in the first segment, we showed that a linear dynamical system could be completely solved, whereas in general, nonlinear dynamical systems are unsolvable. However, there's the hope that the linearized dynamics of a nonlinear system might actually closely describe the properties of that nonlinear system, at least in the neighborhood of a distinguished point. We'll illustrate this again using our damped pendulum back from the previous section. So I'm plotting for you in equation 6. I'm writing down for you again a reminder of what the right-hand side of the differential equation looked like. F sub sp, the function, the field vector, or the vector field as it's called, of the simple pendulum on the right-hand side. At the bottom point, at the bottom equilibrium state, let's evaluate the Jacobian, the matrix of partial derivatives of little f sub sp at q star being 0, 0. And let's plug that q star in to the Jacobian matrix capital F, and let's evaluate it, and that's exactly what we've done in this bottom row. That's the linearized dynamics of this nonlinear system, the pendulum, at its bottom fixed point. At the top, we have the same formula for the Jacobian, but notice that we're plugging in the top fixed point, which is the angle at theta, 180 degrees above ground, above the downward pointing part, and at zero velocity. And when we plug that value of theta in, of course we get a rather different matrix. The same Jacobian matrix, the same linearization function, but it's being evaluated at two very different q stars. First we did it at the bottom, and the second we did it at the top. We're going to introduce changes of coordinates to talk about the normal forms of these dynamical systems, first in general, that is away from fixed points, and then in particular close to fixed points. A change of coordinates is a one-to-one and smooth, continuous function that has continuous partial derivatives, continuous Jacobian matrix. If its inverse function is also smooth, then we'll call it a change of coordinates. And what we would like to do is we would like to write the old dynamics in the new coordinates. To do so, if we're given a differential equation, x dot equals f of x, and a change of coordinate, y is equal to h of x, where h is one of these continuously invertible and continuous smooth functions, then we'll take d by dt of y and we'll use the chain rule to get our hands on d by dt of x. Let's do that. We'll see that y dot, using the chain rule, is the Jacobian of h times d by dt of x. But x d by dt solves the differential equation, and so that reduces to the Jacobian of h times the vector field f. But we can substitute for x in that equation by using h inverse. And so suddenly we have a new differential equation, y dot equals f tilde of y, where f tilde of y is said to be conjugate to f. It's not the same form as f. F tilde is very, very different. It looks very, very different when you write it down. But it has the same properties and the same behaviors in exactly analogous way to the diagonalized matrix capturing the linear properties in normal coordinates of the matrix whose eigenvectors you found to diagonalize it. The normal form of any vector field away from a fixed point is always a constant vector field, simple. It's not to say that the original vector field had this simple behavior, but it's conjugate to it. And so a change of coordinates will make it look simple in that way. We're interested in the normal form at fixed points as well. So what we mean by the normal form is reducing by change of coordinates a function to its simplest polynomial conjugate. The Fobach's theorem, to summarize this idea, says that if you are away from a fixed point, then your dynamics is conjugate automatically, at least in a small neighborhood of any non-fixed point. Your dynamics is conjugate to a boring old constant flow dynamics. The normal form near a fixed point is much more interesting. The Taylor remainder never is going to be of interest to us in this discussion, but the constant term at a fixed point by definition vanishes. We suppose that x star is a fixed point, and what that means is that f vanishes at x star, as depicted in this equation. Now, our leading term is the linear vector field, capital F, evaluated at x star, where remember that capital F is the matrix of partial derivatives of the original nonlinear field evaluated at the fixed point x star. It dominates, and it turns out not only does it dominate, but there's a theorem, the Hartman-Grobman theorem, which I'm going to abbreviate HA, and I'm going to call it the hyperbolic approximation theorem. You have to look at more complicated books to really understand this theorem. But what we should understand is that in the neighborhood of a nice fixed point, the nonlinear dynamics is conjugate to its linearization. Not only is the linearized dynamics dominating, but it actually completely captures the behavior so long as x star has the property of being hyperbolic, which is a fancy way of saying it has no purely imaginary eigenvalues. Again, this is a very long story that I'm just giving a small mention of, and I'm referring you to the legendary textbook by Professor John Guggenheimer and Phil Holmes that is still considered to be the Bible of nonlinear dynamical systems if you become interested in following these ideas. The fixed point at the bottom now, we're being told by this theorem, should be captured behaviorally by the linearized dynamics at the bottom. Well, the linearized dynamics is governed in turn by the eigenvalues, the roots of the characteristic polynomial of that matrix that we just calculated in the previous slide. Let's compute the eigenvalues, and we see that the eigenvalues actually are negative, have negative real part. They have non-zero real part, assuming that we have positive damping. The behavior near a hyperbolic fixed point, then, including the stability behavior, is governed by the linearized dynamics. And so the change of coordinates preserves the stability properties. Continuously invertible change of coordinates takes bounded to bounded sets, so it preserves stability. And it's continuous, and so it preserves limits, and so we preserve asymptotic stability. So the stability properties have to be the same, and so the linearization governs the stability properties of the hyperbolic fixed points. Taylor says linearization dominates. Hyperbolic approximation guarantees that linearization actually determines stability, so that the damped pendulum near the fixed point can be understood behaviorally by looking at its linearization. And here I depict that by juxtaposing the red nonlinear flow against the linearized dynamics of the flow near the fixed points for different parametric values of the pendulum down at its fixed point. Again, we have some exercises where you can do some of these calculations and do some of your own exploring, but we'll press on. In contrast, near and very near the top fixed point, we once again see that the nonlinear dynamics is closely approximated by linear saddles, and the linear saddles are clearly unstable.